I welcome you all to the second video of the aerodynamic series. And I hope that in the previous video, where it was actually said that look for more airfoil by yourselves, I hope that you guys might have become familiar with the term airfoil and you might have searched about what are different kinds of airfoils. But for sake of everyone, and like no one should feel left out, right? So I will actually discuss what exactly is a airfoil. So basically what an airfoil is, it is a cross section of your wing. So how is your wing? Your wing is something like this. Yes, something like this. And if you cut it from anywhere, so a shape will appear like something like this. It can be flat, it can be symmetrical, it can be of any kind of shape. And this shape is called cambered shape. Like we will later on learn about it. Not in this video, in some other video. This video is about something else. But basically, this cross section is airfoil. Okay. So I hope that some people might have actually searched about different airfoils because if you want to learn about all these things, you need to become more curious about everything. Okay. So moving on, what is the aim of the video? The aim of this video is basically to get ourselves familiar with different kinds of terms which we will come across quite a few times in the future videos. So that you guys do not get confused and get jumbled up in all those terms and it can get easier for you guys. So you should familiarize yourselves with these different kinds of terms. All right. So the first term is speed. We all know what speed is. All right. So we will be denoting it with V as we all know. Uh, all right. So basically, it's a velocity of an aircraft, and we will be actually denoting it with V. And moving on, wing area. Okay. So finally, we actually come across wing. So I'll be using a diagram this. All right. So before wing area is basically like as the name suggests, wing area. So this is your wing. All right. So whatever the area it covers, everything. This area is basically a wing area. But I want you guys to understand what is a wingspan and what is chord length. Okay. So basically a chord length and a wingspan. So wingspan is basically this length, this complete length. I will actually draw it. This complete length, if you will see, right? This complete length is your wingspan. So basically the length of your wing is wingspan. So what is chord length? So see here, chord is written, chord length. So this is chord length. So this length is chord length. Okay. And if you will actually later on when you will learn about airfoils, right? So you will actually understand that for airfoil there's a certain chord length, okay, and it denotes the length of the airfoil. So uh, this and this is same. All right, you can see that there's a shape of the airfoil. See, it's flat from the below, and there's a U shape on the above. So it's an airfoil. But we will not go in airfoil. Basically, this length is chord length. Okay, and I have taken a rectangular wing here. In the later part of the video, we will actually learn that there are a lot of kinds of different wings and different shapes. It's not just rectangular. I have taken a rectangular wing for your people reference because whenever we actually imagine a wing, we always imagine a rectangular wing. That's really easy for us. Okay. So aspect ratio. So what is aspect ratio? Again, the same diagram. So we know that this is wingspan. So I will take it as L and I will take it as B, chord length. Okay. So the formula for aspect ratio is span square upon wing area. Span is wingspan only. Okay. So span square, that means L into L and wing area. So what is the wing area of a rectangular wing? L into B. Right. So we just write L into L upon L into B and we get L by B. And if you go on a literal meaning of what aspect ratio, this is aspect ratio, right? The ratio between the lengths of a shape, so of a rectangle. So L by B is the aspect ratio for this wing. But why don't we directly use L by B, and why do we use span square upon wing area? That's because there are different kinds of wings, and it's not just rectangular. Let's say I take an example of like this. It's a tapered wing. You see that the width is changing. The width is more here and it's lesser here. It's wider at the root. That means that now we cannot exactly say that okay, this is B and the aspect ratio will be L by B. No, the width is ever changing. The more you actually go to your right, the more you go to your right, the width is changing. It's getting smaller. That means you can't exactly use this formula L by B. That's why we always have this constant L. L is constant. That's why we can say that okay, L square. But for width, so what we say that we will calculate the area of this shape. Calculating the area is easier, right? We can do it. We can calculate the area of this shape. So we can simply put those values here in the formula and we can get aspect ratio. All right. There are more terms like tapered ratio and different kind of ratios for different kind of wings, right? But we will be encountering them in later videos, not in this video, sometimes. Next is angle of attack. So what is angle of attack? Now here. So as we all know, this shape is a airfoil. Okay, so this is a airfoil. But don't just imagine an airfoil. I will say that try to imagine a complete wing. That's how a wing is, right? Airfoil is just a cross section of a wing. So this is a complete wing, and air is hitting it. Air particles are hitting the wing. As we all know from the previous video, there is a difference in pressure on the upper side and the lower side of the wing, and also the wind particle actually air particle hits the wing, and because of that also lift is generated. But for now, let's actually try to look for what is angle of attack. So this is the direction of your velocity, all right? That's why relative wind, because the aircraft is moving so fast in a certain direction that this is the direction of your relative velocity, and this angle which goes through your chord length, this line is your chord length. So the angle between the line of the chord and the opposite direction of your velocity, and angle between them. So this is velocity and this is chord length, direction of your chord length. Sorry for my handwriting. So chord length and velocity and angle forming between them is alpha. Okay. So this will be angle of attack. In future videos, we will try to understand how crucial angle of attack can be and how it can affect a lot of terms. Really, in the future time, we will actually come to understand that how important angle of attack is to analyze a wing and to analyze a airfoil. Okay, plane forms. Finally, we come on the plane forms. So, as I told you, there are different kind of plane form. Rectangular wing, we all have encountered this. We all have seen this diagram. This is a rectangular wing. You can see this. All right, this complete thing. And what else there is? Tapered wing. As I have already discussed, tapered wing. If we zoom in here, look at this. It's wider near the root, and the width here is lesser. You see this? So the width is changing. So how will we calculate the aspect ratio? We will calculate the complete area of the wing and the length. We'll know already know the complete length of the wing. All right. Then there comes delta wing, and there is elliptical wing. There is swept wing. So in the club, we will be using rectangular wing, tapered wing, elliptical wing, swept wing. The chances of using delta wing is really less. Mostly we won't. We will never use it. But these four wings are quite easy and actually quite fun to work with. All right. And later on, Reynolds number. Now, Reynolds number is quite a tricky thing to actually understand at your stage. But I will be actually uh, delivering you the definition or some like a kind of understanding, a way of understanding what Reynolds number is. So basically, Reynolds number helps us to predict the fluid flow pattern in different situations. Now, like even this definition might be quite difficult. So, what is fluid flow pattern? All right, and what are those situations? So basically, let's imagine a plane which is flying up in the air, right? It's flying, and air particles are hitting the plane in all sorts of direction. But for now, I will actually suggest you to actually imagine a wing, all right? And air particles are hitting it continuously, and the velocity is changing. So that means first situation is velocity. Second situation will be the air density. So I will air density. Okay, density. I'll take some time to write it. My clumsy handwriting. Okay. So one situation will be what might be the velocity, what might be the air density, all right? What kind of particles are actually hitting it? There might be dust particles, there might be air particles, all right? There are different sorts of elements in the air. There is moisture also. So all these things can actually change the way you are actually flying up in that air, all right? So they actually affect your flight, the way the wing is flying and the what lift is it is generating. Reynolds number is quite crucial when it comes to actually predict the pattern of what air might act. Let's say I will give you an example. It's an airfoil, right? So you might have seen this flow diagram, all right, that how air goes, right? So let's say that in one situation, this was the airflow, but in other situation, I will make another airfoil. In other situation, how air was going, air went like, so do you see this? That air particle here, the air particle actually left the side of the airfoil, but here the air particle was following the trail or the curve of the airfoil. But here the air particle got really turbulent and they actually left the surface of the airfoil. So this is during a high velocity. If you increase, the more you actually increase the velocity, this thing actually happens. All right. So basically, we actually use Reynolds number to actually predict what might be the behavior of air particle, of the wind particle, and at what height, at what velocity. And according to that, we try to analyze the performance of your wing and your airfoils. Okay. With the time, you guys will be really familiar with Reynolds number and how to play with it. But for now, try to just understand it. Don't try to learn all these terms that we have discussed here, right? Just try to grasp the understanding and move forward. All right, lift coefficient. Before I even utter a single word, I would say that first try to understand what is lift. In the previous video, we have already seen that thrust and drag and lift, all right? But really in a general way. So for now, I will actually tell you what lift is. Every time I'll be drawing a wing only because like you can actually imagine a complete body of a aircraft. It's on you. But every time I will be drawing a wing because mostly the wing is actually the one thing which is working. All right. So if a wing is which is mounted on the aircraft. All right. So I will from the next time I won't be drawing the body of the aircraft. I'll be just drawing the wing. Okay. So you guys need to imagine the complete aircraft. So if a wing is actually going forward with some velocity and there is some certain engine, it is producing some thrust. So a certain lift is generated. Lift. All right. So this is the lift, an upward force to actually pull your aircraft up in the air. Okay. So a certain lift is generated. So we get the idea. Okay, what is a lift? So now what is exactly a lift coefficient? So to get the behavior of how an airfoil, and because lift is more of actually dependent on the shape of the airfoil also. It depends on the velocity, it depends on the thrust, and a lot of factors, but it also depends on the airfoil. So for an airfoil, what we do is that we try to analyze the airfoil and what might be its lift coefficient and how much lift coefficient it's producing. So this is the formula for the lift coefficient. So whatever the lift force is generated, and this is a constant, and upon v square into s and this lambda. Okay, so basically we got the formula and we can actually calculate the CL. But this thing doesn't matter for us for now. It's just a simple formula. We can actually calculate it anytime if we want. What I want is that simply get an understanding of how exactly we think about CL. So basically, the more the lift coefficient is, the more it can generate lift on a higher velocity. Just take everything that side and keep lift here. Okay. So what we can see that lift is directly proportional to CL, right? CL. Even CL changes itself on different velocity and different angle of attack. If later on you will analyze, a CL is quite dependent on alpha, angle of attack. But in a way, we can say that okay, lift is directly proportional to CL. So the more CL it can generate, so the more lift we will get. Okay, that's how we use lift coefficient. All right, moving further. Same goes with drag. If there is a wing and all the forces are acting upon it, so a downward force is produced. That's called drag. Uh, Later on, when we will be in the future videos also, we will have a quite detailed discussion of how drag is being produced and how it can be reduced by taking different form of shapes and in different situations and a lot of things. But for now, the same explanation, just mirror it. So the same thing, total drag and CD. So you can see that, okay, even drag is directly proportional to CD. So we can't exactly calculate how much the drag might be, but we can always check the pattern and the behavior of the airfoil and the behavior of the wing. And thus we always try to go for CL and CD. Okay, such coefficients which are directly proportional to lift and drag. So we can actually predict what might be the behavior and how much lift and how much drag it can produce. Same with CD, drag coefficient. Okay. So these two terms are quite important. I would say familiarize with yourself with them and don't get uncomfortable while thinking about it. Okay. These are just terms. Just try to understand it. Don't try to memorize them. Okay. Next is moment coefficient. As in the previous video, you people might have seen a diagram where thrust and all the forces were acting upon lift, drag, thrust, and everything. Okay, so this is basically the formula. Again, I'm saying this. So we can see that okay, there is something called pitching moment, and it is directly proportional to Cm, which is moment coefficient. All right. So first of all, what is a pitching moment? So we can see that in an aircraft, when all the forces are acting, and due to all the forces, there is a certain momentum generated in the plane. Okay, so this is the center of the gravity, and here only like we can take it. So a certain momentum is generated due to all of the acting forces, and that's what we call pitching moment. So even this torque, this pitching moment, is directly proportional to Cm. So, as I have already said it twice, I'm saying it thrice. We can't exactly predict the pitching moments, but we can actually predict its behavior and how much it might be by Cm because it's directly proportional to it. Okay, moving further, stall. So, stall point. You will always hear stall point also. Let me write point. Point. Uh, okay, stall point. So, what is a stall point? Let's say that your aircraft is flying and there is some certain height that it reached. Okay, and you will see that every airfoil can produce a certain CL, all right, lift coefficient. That means if it can produce a limited amount of CL, it will only produce a limited amount of lift. Okay, lift. You guys can understand that this is lift. So, and you have your engine which can deliver some certain thrust. That means even your velocity is limited. And when everything reaches their uppermost limit, lift, you have reached your max velocity which your engine could have provided. So you will touch the maximum CL which your airfoil could have provided. Then you will actually see that all the forces will come to a balance. All right. And you will see that your aircraft is basically stuck at a similar at the same height. You cannot go any further. You can only come down. You cannot achieve any further height from that plane. Even your angle of attack, by increasing angle of attack, you get more CL. All right. We will actually learn the pattern of the CL. It's not exactly every time to increase the angle of attack and your CL will increase. But for now, because at some part it actually acts like this. For now, I'll say the more angle of attack you increase, the more CL you generate. So the more CL you generate, the more lift you get. All right. Here, velocity, we will take velocity as constant because we are assuming that it's at its highest velocity. Okay. So now let's say that, and after a certain increase in alpha, your CL starts to decrease. So let's say that at 12 degrees, we got the maximum CL that we could have achieved. So at that point, we have the maximum lift. So now we cannot further increase the lift force that we were producing. That means now there's a point that you cannot achieve any further height. And that points, my friend, it is called stall point. Okay, stall point. And with that, I would like to conclude. We have familiarized ourselves with quite a few terms for now. So I would suggest don't try to memorize them. Just go through all the terms, and we have come across quite a few terms. I will again kind of revise you guys. Speed, the velocity of your aircraft, wing area. This is the wing area. This is the wing span, and wing chord. This is your chord, and this is your length and aspect ratio. We realized the importance of the formula. We cannot exactly directly use L by B. We need to use this formula. So you can try to learn it or try to understand it. Angle of attack. We realize that, okay, this is an angle of attack. And the behavior of angle of attack, we will actually learn it when we will be understanding the airfoil. Because see, airfoil is quite important. Understanding the behavior of an airfoil is really important. Okay, something happened. Yes, understanding the behavior of airfoil is really important, and the later future videos we will be learning airfoil. Plane forms, we learned different kinds of plane form: rectangular, tapered, elliptical, swept, delta wings, and Reynolds number. Absolutely, Reynolds number was quite important. And then lift coefficient, drag coefficient, movement coefficient, and now the stall. So these were a few terms that we will be actually encountering a lot in the future. So this time we familiarized ourselves, and in the upcoming videos, we will be actually talking, having deep discussions about airfoils and their behaviors. All right, and how and on further later videos, we will be seeing how to select the airfoil, how to select the wing, what will be different kind of plane forms, and why to select different kind of plane forms, and a lot of things. So for now, I take my leave and really thank you. Thank you for sitting by and watching the video. Thank you.